A map is like a function, but instead of taking in numbers and putting out numbers, a map, which we will write with capital letters, takes in points. And in this case we will study points in a plane, so 2 points with 2 coordinates. So it takes a point and maps it out to another point. So we can call it set W. An example of a map takes the first coordinate and make it twice as large, and the second coordinate square it. So what does this map do with the points? So let's take some example here. What happens to the point 0, 0? It will be mapped to this point, which is 0, 0. So point 0, 0 will be mapped to itself. And if we map the point 1, 1, it will be mapped to the point 2, 1, and so on. So we can map different points. We see here that the point 0, 0 was mapped to itself. The point 1, 1, it was mapped to 2, 1. The point 1, 2 was mapped to 2, 4, or will be if you calculate it, and map to 2 to 4, 4, and so on. So we see this, all the points here on the green square, for example, they will be mapped to the points here on the blue rectangle. So all the points in between here will be mapped to points in between. So you see this figure will be mapped to another figure. A congruence map is a mapping that maps figures to congruent figures. For example, if you have a square, this will be mapped to another square with the same size. So the original figure and the figure we get after the map, they are congruent. So the same shape and same size. So for example, if you have a triangle with a certain shape, then this will be mapped to a congruent triangle with the same shape and same size, so that they are congruent. So that is a congruence map. And congruence map, there are either rotations, so they rotate the figure. So when you rotate the figure, it keeps the same shape and size. Then we have a translation. And the translation moves all the points. So all the points here are moved with a certain vector in some direction. So all the points are moved in the same way. So we end up with a figure that is congruent to the original one. So that's another example of a congruence mapping. We can mirror, to mirror the image. So if you mirror in some line. So for example, if you have this figure, then this figure will be mapped to a figure that is congruent to that one. So to an identical figure, even if it maybe not look like this because it's a sketch. So these two are supposed to be identical, just mirror image of each other. And the last one is a combination of a translation and mirroring. So if you have, for example, you have a line that you mirror in, and you have, for example, a footprint. Then first you mirror the footprint. Then you move it with the vector. So it ends up like this. So first you mirror it, and then you make a translation of it parallel to this mirror line, the line you mirror in. So let's take an example here. This mapping pxy given by x plus 3, y plus 1. That is an example of a translation. So you translate all the points. And in this case, you move all points 3 steps to the right and 1 step up. So for example, the origin 0, 0 will be translated to the point 3, 1. Since all points are moved 3 steps to the right and 1 step up. So if you start with this figure, you see that all points on this figure are moved 3 steps to the right and 1 step up. So this whole figure is translated with this vector 3, 1. Another example is this mapping, defined like just switching place of the two coordinates. So the x coordinate becomes the y coordinate and vice versa. So for example, if you take the point 1, 2, it will map to 2, 1. So what does this mapping do? Well, if you put in points in a figure, you will see that it will take the mirror image of all points in the line y equal to x. So if you take all points, for example in this arrow figure, they will be mapped to this. So this is the congruence mapping, since the shape and size is the same. It should just be mirrored in this line here. So this mapping is an example of a mirror, taking a mirror image in a line. This one, this map defined like this, if we switch place of the two but also switch sign of the x-coordinate, what does this mapping do? Well, if you put in some numbers to investigate what it does, for example for 1, 1 it goes to -1, 1. For 1, 2 it switch place, so you get -2, 1. So the y coordinate here becomes the x coordinate with the minus. Or for example 2, 1, the x is 2, so that becomes the y coordinate here. And this is -y, so this -1. So if you put in some points here, you'll see that this corresponds to a rotation counterclockwise 90 degrees. So this mapping here does the rotation counterclockwise 90 degrees around origin. So you see that this square here will be mapped to another square. So this is also a congruence mapping. If you would have changed the sign here, so you put, instead of minus sign here, you put it on the second one, then you will have a mapping 90 degrees clockwise instead. And as we have already commented on, if you combine a translation with mirroring, then you will have example like this. For example, if you translate along a line, in this case the x-axis, and you mirror in the x-axis, you will have this combination. In Norwegian it's called glidespeiling. So you have this figure. For example, this mapping is given by the following formula. So you take x plus 2 minus y. So you see that the y coordinate is mirrored and the x coordinate is translated 2 steps to the right. So this is a combination of the translation and the mirroring. So that this is a combination of this mapping and this mapping. So if you combine these two, you will get that one. And that's the next thing we want to talk about, how to combine mappings. So if you have two mappings, A and B, you can combine them. So let's say that you first put in your point in B. Then you will get out a new point. And then you put in that point into A. Then you have combined the two mappings. So you say that this is a mapping of B followed by A. And you can write this also, just another way of writing it. You write it like this. This is a combination of two mappings. So you first take B, and then you take A. For example, you take a point AB, and then it maps it to AB squared. And then it's followed by another mapping that takes a point CD and maps it to DC. Then the combination of these two will be, if you take a point XY, another way of writing this one is this. This just means the same thing as that per definition. So this is, first we take B squares the second one. So it takes X y squared. And then we take A, which switch place of the two. So we get y squared x. So the combination of these two mapping does this. Then we could of course do the opposite also. We can take first A and then B. What would we get then? First use A and then put that into B, like this. So if you first take A, we should switch the coordinates. Then we'll get y, x. And then we should square the y coordinate. But now here, x here stands for in the place for the y coordinates. So that's the one who's going to be squared. So we square that one. So even though it's called x, that is x, that is the y coordinate here. And y here is the corresponds to x coordinate. So this will be the final answer. And you see that the outcome of taking first B and then A doesn't give you the same thing as first taking A and then B. If x and y is equal to 1, they will be the same. But in general, these two will not be the same. So that means that mappings, so if you combine two maps, they will not in general be commutative. So you can't just switch the order of two mappings and expect them to give the same result. Some mappings will do, but in general they will not. For example, these two it didn't. Let's take another example. Let R be a rotation 90 degrees counterclockwise. And let S be a mirroring. We mirror in the line y equal to x. We now want to show that the order of doing these two matters. So if you do first the rotation and then the mirroring, or we do first the mirroring and then the rotation, it will not necessarily give the same result. To show that these are not the same, it's enough to show that they are not the same for one point. Here we see the result of first doing the rotation. So we take a point, rotate it 90 degrees counterclockwise, and then we take the mirror. Then we get back here. However, if we switch the order, if we first do the mirroring from this point, we get up here, and then a rotation counterclockwise 90 degrees, we'll end up here. So we see that if we take this point here, they will not give the same outcome, these two. So that means that they are not the same, since there exists a point which to give a different outcome.